Wow. Okay, so this is huge. Now we're at the normal equation. Lots of things are happening. This is great. We have to calm down a little bit. Okay. T-shirts. Always getting the T-shirts. So that's happening. But this is where we are. The amazing normal equation. So turns out a pretty simple transformation of ax equals b cleans everything up. And it's weird. I think it's pretty weird. You should understand it, but I think if you started, if someone presented this to you at the start of the course, it would seem a little odd. Everything does. Okay, all right, fine. So this is the game. We're trying to find the best approximation to ax equals b when b is not in the column space. So this builds from this projection piece we just did. Before, we just gave up, right? We just gave up when there was no solution. This betrayed a lack of ticker. So we're going to toughen up a little bit, and I don't know if that's the right analogy. Anyway, so we're going to pull ourselves together and get over the fact that we can't find an exact solution, because that happens a lot. And I have a little example coming with fitting a line to some points, right, which we've talked about in class, or should have talked about in class. It's a great example of a very basic ax equals b problem where always you will have no solution available, no exact solution. So we're going to do this. We're going to find, new plan is this, find x star. That shouldn't be up there. I'm going to try to keep that down the bottom. Strange. So we're going to find, this is going to be the notation. It can't be the same x, right? It's a special x, so this denotes that it's an approximation. So that's the idea here. It denotes approximation. It's used fairly commonly as an asterisk. So we want to find x star so that x star is as close to b as possible, right? Let's highlight that because that is a big deal. This is our plan. And mathematically what this means is we want x star that minimizes this difference, right? So this is the distance, the double lines here, right? Means the distance between b, I know it's exciting, b and ax star. So what do we know? We know b, we know a, we know b. We're trying to imagine sort of traveling around in x space, and we're trying to get as close as we can to b. So that's, right, this is the best we can do here. This is where we're trying to get to. And this is the error here. Okay, good. So projection. We have a column space. We have a left null space. We have a left null space. It's a strange place. I can't even pronounce it properly. Right? Goal in life is to make left null space as small as possible. So we're going to do the same thing. Use the same notation, P plus E, right? Projection of B will live in column space. We want this. And we want the error to be in the null space of A transpose or the left null space. And we know those things are orthogonal, right? This guarantees, if we find this guarantees, lots of guarantees, free tofu knives, guarantees this, that they'll be at right angles. And so just as we've figured things out, we project B onto the column space of A. We've done it just for a line. We'll see how we can do this more generally. And then we'll solve this problem. Right, we're going to solve this instead. Okay, so let's do it. Sneakiness. It's the same approach as for simple projections, right, onto a line. So we want B to be P plus E. We need this to be true. And we need this to be true. So let's give them numbers, I guess. Why not? This is 1, this is 2, and this is 3. So this is monks who really are eating too much, I'm afraid. And they like the orthogonality thing. So we can really work with that. It's always good to have something equals 0, right? Which is what you should be thinking about for a net calorie intake. Okay, so they're pretty rude, actually, for monks with the whole piousness. Okay, so I think there's some psychological research on that. Okay, so let's see. So we're going to say this is true to start with. So this is 3. So we're going to start with 3. 3. This is true. We know that this must be, we're requiring this to be true, that this is B minus P. So now we've used 1. True facts of the matrix. And now we've used, now we're going to say this is A transpose B minus, just spreading things out, P. And now we'll use 2. Okay, so 2, A transpose. Well, before we do that, let's just put these things on the opposite sides, right? So this is going to be A, so this means A transpose B is equal to A transpose P. Transposes, right? Wow, it's amazing. You should be amazed. Okay, so that's A transpose. Let's get this next piece. Sorry about that wobbling around. So this is 2. We're going to use 2 in this little equal sign. It's a sad 2. Make it a cool 2. Cool. Okay. So this P becomes, it has to be some combination of A's columns. That's really what that says. A x star. P has to live in column space, which means it's some combination. Right, so this is P. It's a mathematical way, means P is some combination, linear combination. Such beautiful poetic words of A's columns. Poetry. That's what you think about when you think about matrixology. What is this craziness? Let us turn it around. Let us turn this around. So we're going to group these pieces here. Let's think about the sizes of them. Well, I'm going to switch sides. So we know what happened there. This is A transpose A. Let's make that nice and big and juicy. This is an X. Might not be juicy. But big. Okay, A transpose B. Yes, and so this is M by 1. This is N by M. I need to stop doing it. This is N by M. Maybe that's a solution. All right, so, and this is M by N, using our conventional dimensions. Right, so these match up. A transpose A, great matrix, right? It's symmetric, it's square, symmetric. And we haven't seen anything yet about how great that is, but it's going to be completely awesome when we get to eigenvectors and eigenvalues and eigenstuff. Good. So this whole thing here is now, this is an N by N. This is a M by 1. And this thing is an M by 1. So we've got a square matrix times a vector in Rn equals some other vector in Rn. Right, so this is an element of Rn. This is an element of Rn. Yes. Goodness. Okay. So this is really a vector over here. So this is called the normal equation. If you broke it into pieces, I'm just going to go back and color it. I'll have to give out the underlying blob for all of this, the underlying GoodNotes file. I'll do that eventually, so you can blow it up. Okay, and this is of the form what do we see? Of the form, it's something, it's some matrix times x star equals b prime, right? n by 1, n by 1, n by n. So these are primes, right? The idea is this is some other modified thing. So this is amazing. It's amazing. It's amazing because it has all the properties we want. It's solvable. X star is in the column space of this blob because we made it happen. It's a requirement of what's happened here. You could, oh, right. I'm not going to say anything more. So this is always solvable. Incredible. It's always solvable. And it's not too hard to make, right? I mean, depends how big your matrix is, and there are some problems with numerical things, but that's not what this course is about. You should do numerical methods as well. But pretty fantastic. So you take your original AX equals B, you simply multiply the B by A transpose, you multiply by A transpose. We have a new system to solve. You solve it, and then you can come back and whatever X star you get, that's P, right? And we should be able to see all of that. But this is the solution that will be will give us A times this solution, A times X star will give us a P, which is as close as we can get to B, right? Because the bit we're missing is here. The bit we're missing is this. It's the error, right? And that is only, it lives in left null space. There's no way we can make that. We can't make it. Can't make it because we understand things. We have the knowledges. Okay, so the big picture now starts to look like this. It's just the abstract one. We're going to be very, so actually in the what's called 14 will be the detailed one. So probably have to shuffle them. Yeah, so we've got P. Sorry, actually we've got B. It doesn't live in column space. We break it into two pieces. We break it into the part that lives in left null space, the part that lives in column space, and then we solve this problem. AX star equals P. And we go by getting the requirements that E is in left null space, that P is, by including those requirements and on top of that P plus E has to equal B, we arrive at the normal equations, right? So this is the thing you solve this. You solve here, right? So we solve this. Solve the normal equations to find X star. Right? We're not going to solve this. We're solving the normal equations, right? Okay. So that gives us an X star which must live in the row space. Well, it gives us an X star which it may or may not live in the row space. True. So let me move that. I think I'll clean that up. Yep. Let's get this right. So we cannot make B, right? So we give up on that. But we get a solution. And I think I was using blue. We get some solution. And we can always, there's a null space issue as well, but that's not what we're thinking about right now. X star. So it could be part of column space. We haven't quite talked about that yet. But there'll be a part of it that is an x, I'm going to call it x star r, and then we can always add x star n. And this is the good stuff, right? So this one gets sent to P. I think I want to get rid of that. Yeah. Okay, good. So this is solvable. This is never solvable. Right? We can never get this. It's got a part that lives in left null space, unmakeable. We find the part that lives purely in column space, we get a solution for it. Again, it's a general solution. It will have a part that lives in row space and a part that is in null space, if null space exists. So all those things apply. So it's a beautiful solution to this problem of having no solution. We are guaranteed to get the closest possible vector P, right? It's the closest we can get to B. So, and that's fine. Approximation is a good thing. Again, we'll have an example next about fitting a line through a bunch of points. Really basic kind of thing to do. You can do this with calculus, which of course is evil and wrong. In calculus, what you would do is try to minimize, right? So you differentiate it. You set up a function, which is really this squared, for example, and then you'd minimize it. And you differentiate, it's multivariate. You differentiate with respect to all the pieces involved, which, depending on what you're trying to model, here it's a straight line, so we have two variables. You differentiate with respect to those and find the minimum. Right? You minimize the distance. So that makes sense. But there's a beautiful picture here, right? It's a beautiful kind of understanding that we cleave off the part that is simply unmakeable by A. We're left with the part that is makeable. We build that, and we're done. So you should be feeling fantastic. So a job in life is to move everything that you have in left null space. I mean, now we're being silly, but left null space into column space. So let's put this into column space. Right? That's the idea. You want to have a nice big healthy column space because they're all your little building blocks. Things sleed into you. You can capture them. Now we're being, this is not matrixology anymore. But the stuff that you can't get, that's here, right? There are the known unknowns, and that's kind of what we have here. Unknown unknowns, they're bad. So you have to be really very, very, very thoughtful about those things. And you do not want to win any Dunning-Kruger awards and then also not understand why you won that award, which I guess you wouldn't. Okay, all right, but anyway, back to this. The normal equations, great. And mechanically, there's no problem with doing it, right? You just have to take A transpose, multiply it in, and then you solve it just as we've solved these equations in the past. It could be LU decomposition, whatever you need to do. If it's very small, as in the case of fitting a line to a cloud of points, it doesn't matter how many points you have. When you do that A transpose A, you will end up with a 2 by 2. Very easy to solve. Okay, so onwards.